Before we now start taking a closer look on cycles, I want just to show you in a very short overview some of the freeware render engines that are available for Blender. So we have a quick compare. So first we have the Blender render. This is something you may know, and it's fast. It doesn't have so many features, but it works very reliable. In about 1 minute, I expect us to get a nice looking 3-dimensional dragon here using Blender render. And I think some of the tweaks that we do later in this video with Blender cycles may also be interesting for Blender render. For example, increasing the number of threads. I could imagine that we can possibly also get a little bit time improvement. So, but now we will take a look on the next. That's a Blender game. I expect that we get the same result here, so there will not be a significant difference. A pure CPU-based renderer doing a very fast job, and the Blender game seems, in my tests, often to be a little bit faster, even if it looks the same like Blender render somehow. So let's go to cycles, and this is where we will take a closer look on optimizations later in this video. So when preparing, cycles is really fast here, and when rendering with the default settings, it's also really fast. Like you see, it even easily beats Blender render by a tenth of the time. And we have a nice black and white 3-dimensional looking dragon here. So next in our test is POV-Ray. POV-Ray is an external program, so this will take a while, depending on the complexity of the scene, to export the mesh to POV-Ray. And I guess this alone will take a minute in this process, because this dragon is relatively large. When POV-Ray starts up, you see this window, and this just means it starts rendering. I guess this has been 2 minutes, and now it's first passing the tokens, also it's reading the mesh files, and they are really large, I think. So this again is taking a while before it even can start to render. Generally about POV-Ray, it's one of the most stable programs in this, from this freeware rendering programs. It's a very old community, so it's one of the first rendering programs. It was available on the Amiga already, also on the Commodore Amiga, before even the PC era, and it's pure CPU based, but that's also one of the few disadvantages. Besides that, it has a very easy to learn scene description language, SDL, and it's a really nice tool which I can recommend. Also it has far less crashes than most of the other renderers. I would say that it nearly never crashes, whether you get an error message or you get normally some output from this program, while even cycles, which is are mostly stable, sometimes brings error messages about memory allocation. You will see this later, especially under Windows 10, or it will crash and take the whole Blender into computer nirvana. So this is never to be happened with POV-Ray. It's a very stable program, and it's a very solid program. Therefore, it has no GPU support, and that's its advantage. So you see the parsing again takes a while. So we are not like 15 seconds in this time like with cycles. Anyway, we can possibly take a look so long about POV-Ray. So this is getting a little bit informative in case you want to add it to your renderer selection in Blender. So there's the official POV-Ray website, where you can see also some pictures that are made using POV-Ray. There are several artists who use POV-Ray, one of them, for example, here. Many of the scene files you see here, you can even download and try them yourself. So how far are we? Did not yet start render, he's still parsing. When POV-Ray starts rendering, we will see it here on the right side. So this is the help file that comes with POV-Ray. Mostly, I have to say, you use POV-Ray by the scene description language. You don't maybe use Blender or something, but you just type in what you want. This is a little bit a different system. It's also from the earlier times, from let's say pre-PC times, but it has advantages, especially in visualizing technical data, because this way you can even automatically generate these description files and have the results of your experiments, of your scientific work, rendered into three-dimensional pictures easily using POV-Ray. And that's one of the points where it's actually most used, I think. So at the moment, this program is busy, so we can still take a look at the pictures so long. Really some pictures where it's hard to say, are they real or are they rendered? So there are a lot of, I will just load one of these files. No, I think he's really busy. He doesn't load me a lot of these files. Fishes. Oh, he used Win3D, for example, to make such a fish. Okay, old fish. So gears. Nice work. And you can even download the scene file and make your own stuff out of it here using POV-Ray. How far are we? For some bolts, they are really nice here. They are not real bolts, they are just rendered. Apples. These are really nice apples. Another advantage that you have when you use an SDL, Szene Description language, is that you can make a script that will generate such landscapes by random formulas. So this is what he did here, is some terrain generator. So he can even generate a terrain and render a photorealistic picture out of it, just using one program. So now I close this. I better let it render. So you see, he is really taking a bit time to render. We are not ready in 15 seconds here because it's a large mesh for him to render. I see. How is the memory usage? 8.5 gigabytes. So in the meantime, we can take a look on the SDL. So the POV-Ray program now started to render. That is what we see here. So currently we are still rendering using POV-Ray. And where do I have it? Here is it. So my recording program. What we see is that from the material that POV-Ray has taken here is even transparent material. So this is maybe one of the reasons why he is taking a lot of time here for rendering. The CPU usage is on 100%. Memory usage is on 7.6, that's rather moderate. And he is also making a nice three-dimensional dragon. So what we see is that, and this is true for all of the renderers, we use, this was originally a Luxrender file, and if you really want to render it with one of the other engines, you would normally optimize the materials and the lighting a little bit, because that's not interchangeable because between the different rendering engines. What I wanted to show is just a little bit what changes from what happens if you choose another rendering engine, rendering system. And this is POV-Ray, an external renderer, CPU-based, very stable. And with a SDL, this means Szene Description Language. This means most users don't use it via Blender, but most users just type in some things like, for example, make a ball or make a light at this place, and then it will render like this. It's nearly the same and unchanged since the times of Amiga computers. Not the program itself, but the scene description language. Actually, they do talk about making it a little bit modern and renewing it. But it's still very popular, especially among scientists and people who make scientific work with mathematical results. While there are also some artists who like it, especially those who do not much to draw and paint things using three-dimensional modeler programs, but do just like to type in what they want at the end. So we are nearly at the end with the rendering. Just two places left, and maybe a little bit more because CPU usage is already on 6 cores actually. So now it goes down, goes up again. So this shows us the last part still being rendered. It's really funny. It didn't take a solid material. It rather looks a little bit like a ghost. So it's a little bit transparent, yet it's not so much reflective. So just like it's a ghost from smoke or something. At the same time, if you look into the POV-Ray program, you see that here the green line is at the very right border, and this means he is ready, and 99%. And this means he will soon start to save the picture, and then the picture will be transferred into Blender. Oh, now I can even show you such a file, how this looks in the SDL scene description language. So mostly there are commands and then a version command and then some global settings, and then the camera position in the three-dimensional space, camera, location, look at, angel, then the light sources, a background, and then the geometrical data, and that's all. That's all. More, you don't need to type more, and then you get a POV-Ray file. Not just this dragon, but something that renders to a three-dimensional picture. So this was it, and here is the result. This dragon rather looks a little bit like a ghost. So this was POV-Ray. Until now, I would say it took the longest time. Let's switch to Yafaray render. I've not done very much with this also rather old program. Some people say it's a little bit of dead. You see there are multiple options how you can render. Mostly bidirectional is the strongest lighting method. Direct lighting is the fastest. So render into Blender. I don't know much about the options. Does he support GPU rendering? Acoustic photons. I could say photons, but we don't really need them at this place. So we will just use it for render. I press F12. Let's see what happens. So from what we see, it says setting up renderer. This is here, and it's always the same. At this time, the Blender Yafaray interface converts the Blender three-dimensional data into the scene description that this render engine Yafaray can handle. And when he's ready, it will start render, but it's not yet. Oh, we started rendering, and this is also nice, also and fast. Besides that, what we see is that at some places we have even the same colors that we had before with Blender Render. So this seems to be even a little bit compatible with Blender Render. So we have a nice dragon, okay. This was fast, really fast. I want to give it a second chance and use the bidirectional engine and look if it changes something. So again, it's starting, and bidirectional. I think we would need to change the parameters about passes here to get a really good picture for this rendering mode, because this is not so perfect. Also, what I don't see anything about GPU support, so this also seems to be a poor CPU rendering program. As said, I didn't use it much. I have just installed it and not much tested it. So let's take a look, before we come to Luxrender, let's take a look at Mitsuba. Mitsuba has also a lot of presets here. Where are they? They are here. No. Where are they? Here. So there is a lot of possible rendering methods. Some of them have just crashed, have to say it like it is. Some of them are maybe working, I don't know. So which one to take? I just leave the direct illumination, which is default, and press F12. Mitsuba, similar to Luxrender, has the possibility to render external or to render internal. So maybe I should have chosen internal. If I choose external, oh, it didn't do anything. I don't see anything. I press internal, and is something starting up currently? No, it doesn't look like it does something, so I press F12. Nothing happens. Okay, then I choose just the next path tracer. I press F12, nothing happens. So what's wrong with Mitsuba? Let me see. Also, again, let's try again. External. Normally, Mitsuba GUI should now be starting up. We will see if this happens. Okay, if something with the renderers does not work, you need to go to User Preferences, go on Renderers, here, Rendering, and here's the place to look what's wrong. So this should be the path to Mitsuba. Is it the path? So I take this path. I put it in a window. And I see here is the Mitsuba. So it's starting up. So generally, this looks like it should be working. generally it works. So that's interesting. Even in the GUI you can walk around and here have it rendered immediately new. Also it has some interesting aspects. Open. What else do we have? This one. Another file. No, this file is not available. Okay, also normally it should work. The path should be okay. If I show him now the Mitsuba exe. Okay, also the path is okay. Maybe because I was using other renderers before, I have to start the thing new. I should try Wi-Fi. Save user settings, refresh, close. So F12. No, I don't think he can start this up. Or possibly it's a problem of Windows 10. I have had this before, that Windows 10 for some reasons doesn't allow him to even start the Mitsuba renderer. So I had this with other programs before. Also it worked with Windows 7 now. The Mitsuba is not starting, and I will have to take a look why it's not running and why it's not working. Possibly this is a problem of Windows 10. Also maybe I have some data here where not much there, where I can show a little bit. Recent, there is a material preview. Ah, this one. Okay, what else? This, is it available? He found some sort of dragon. I don't know when I did render this, or was it the right one from now? So he's loading the thing. So now he loaded. Ah, no, this is another dragon, which is included with the Mitsuba renderer. So I will move it a little bit around. Oh, I can really rotate it. Look, that's funny. And he will immediately, when I leave it, it will start to render this. Oh. Maybe, yeah, I was too much. So I saw, yeah, it's a nice program. And seems to be fast. Okay, but as said, from Blender doesn't yet work at the moment. So we'll have to check why, but this is working fine at the moment with Windows 10. With Windows 7, I had bigger problems with Mitsuba. Also, this Mitsuba brought me an error, also error message when starting. This is not more happening, so not bad, not too bad. So here at the settings, can I change the settings? Block size, worker priority, navigation standard, sensitivity, search path. It also seems to be able to make a network rendering. Okay. Mitsuba itself also uses XML files for scene description. I don't really know where they are. So would have to look for that first, but it uses some sort of XML files for the scene description. So okay, that was our short tour on rendering programs. Now the last one is Luxrender. It also have a lot of different options. So the most important thing is you can choose here between the classic API and the LuxCore API. And the difference is at this time, while I'm talking, the classic API is the only API that supports spectral rendering, also so rainbow effects and like this. While the LuxCore is in several parts faster and more modern, and is the one part that is actually developed. And this is the one that that is able to do spectral rendering. So we can take a look if he can render this. I didn't try before. Originally it should have been worked somehow. So I press F12 and it says exporting dragon. Starting Luxrender and render session object has no attribute, is in pause. So this normally means, when you get this error, it normally means that you have to go to user data again. Where is it? User preferences. Then go to renderer and go to Luxrender and press this update and this update button. So I did all of this and I still get this error. So I did this and still get this error. So it must be something else. So normally I even have to restart Blender. Okay, I can try that. So I have said, so we are back. I have restarted Blender after pressing the update button, and if I press F12, let's see what happens. Starting Luxrender and render session object. Also at the moment this LuxCore thing doesn't work like it should. Okay, so I take the classic and I choose internal, and then here I say he should, I can choose between the CPU and the GPU renderer. At this place I choose the CPU renderer because I had trouble with the GPU renderer, so it didn't work. So I use the CPU renderer and we'll see if we get a result here. So I pressed F12 and what happens? Nothing. Okay, I choose another one. Press F12. So let me check if my settings are right. Okay, yeah, I will tell him he should put it into the image editor. So is this an image editor? Yes. So something should happen, nothing happens. So I don't know really why it doesn't work at the moment. Maybe similar problem. So now I choose the external renderer, and I can show this. I choose the classic API and I choose the biased pace OpenCL, the fastest. So I started. So nothing happens. So at this point, I don't really know why I make direct lighting. That should be rather easy and is only CPU. I press F12. So again, nothing works. So this is a problem. I have also posted it in the forum from Luxrender. If the scene is very large, sometimes just nothing happens. So to not be unfair, I will try to load another scene which works and is possibly also large. So to show you that generally this thing works, what can we take? What's this? Yes, so you generally see how this program works and that it works and that it's also mostly really fast. So just the other file with the dragon, he just doesn't render the thing. So doesn't mean this is a bad program. This is very important. So I will just press render and this is what normally happens. Okay, the LuxCore API, this seems not to work at the moment. I choose the classic. Yeah, this is what normally happens. So you get this GUE here, and then you see here is a CPU rendering, and then it's starting up to render. And then you can also check how your lighting is. If you choose here linear, and then estimate settings, then you can see the lighting in this file is okay. And then you see this will render for some time. So, but in this case, I will stop it and end it. And choose something else. I will choose Luxcore Bias Path OpenCL because it's really fast. So in this case, it will use the GPU. You can see this here. So now first you see the GPU load going up. So it's coming. So if you look here into the GPU load, it's going down to 0. Yeah. Zero. So this is a small problem I have with this thing here. In this mode, it stops rendering. While it says it's rendering, the thing doesn't do really much. It says it has 5 threads. But not much happens, so we try something else. So close this. Does this work internal? Because internal it should work. So internal, I have now set from external to internal. Pressing the middle mouse button, I can move it around. So there's now 1 minute and 8 seconds before we get the first picture. The amazing thing is that it's rendering with 5.90, say 5, even 5 mega samples per second. So that's 4 million samples per second, and that's really fast. So this is the fastest mode from Luxrender, is the LuxCore Biased Path OpenCL in my tests. I don't know how fast it renders with CUDA. So under OpenCL, this is by far the fastest mode. In my tests, it only works in the internal mode. And as you will see, the LuxCore doesn't work always. So this internal mode, it works, and if you make internal, it doesn't stop. Also it will even render this picture until it looks better. So let me use this rendering time a bit and show you a little bit the surroundings. Important is that you sometimes look on the GPU usage. I have 4 GPUs inside, so you see they are on above 90% load. This means 92% load. This means the program is working. Here all 4 GPUs fully used for rendering. And of course you need to always look a little bit at the temperature, that this GPU doesn't get too hot, because don't think this is a computer game. So rendering with Luxrender and often also with cycles, the GPU get much more hot than in a normal computer game. Also it's much more in use. And that's why you hear a fan at my left side. Because otherwise the temperature would go above 90 degrees, and that's what I try to avoid for this graphic card. So now I want to show you some other pictures that were rendered using Luxrender. So you can get samples for that material. So here's one, for example. Can I make this larger? So you can see it better. Here is a very nice rendering. This is also in Windows 7. You had this picture viewer, and you could also zoom inside to make it a little bit bigger to show details, but I don't see this option here. So it's a really nice material, and it's hard to say is real or is computer graphic. And this is the strong side from Luxrender. The backside is, not so strong side is, that you need to really find the whistles and tricks how to make it work on your system. There is one more thing I want to add. So while the biased path OpenCL is by far the fastest rendering way, the best rendering, also with the highest quality, is the LuxCore bidirectional, and is only a CPU rendering. And this also, and this means you will have to take a little bit time, but you will get the highest quality. So I will try this later, and maybe I can have a better picture of this a little bit later. I have now restarted the rendering with the external renderer, because using the bidirectional mode, and yeah, you can use the external renderer. You have advantages because you can close Blender. You don't need it for that. So can go out of Blender, do something else, and Luxrender will render it, and you can later save the resulting picture file here. This is a CPU render, and here you can also zoom in to take a look. I have now a little bit increased the resolution, so we can better see the different results. The Luxrender community is active, also they are developing the program constantly, and they have a very good user support. You can ask questions in the forum, and they will help you if you have problems. So here you can see, for example, the different rendering modes, the bidirectional mode, what we take, and for example, the different results. At the moment, it's a little bit slow because we are using the CPUs for rendering, as you can see here. And in this time where the CPU goes down, Luxrender uses only few CPUs to paint the picture and to save the picture. Also, Luxrender is able to continue a rendering. For example, if your computer crashes or something, you can go here on load FLM file, and then you can continue a rendering that was interrupted before. So this is the Luxrender forum. It's recommended if you use the program. You can get help here and a lot of informations, and also post problems. And these people here, they are very active. They answer your questions, give explanations, and they are really patient. So this was our small excursus to the multiple rendering options in Blender. I hope you like it, and now we come to the next part of the video, the cycles rendering engine. Later edition about Mitsuba-Render. I have tested a little bit here and there, and not sure why, but I can show you the effect if I select Mitsuba with this rather difficult thing to render, and I press F12. It says nothing and nothing happens. If I now go here and say open something not so difficult, okay, and press render, okay, we choose something even less difficult. I make new, reload startup file and press render, and then it works. So actually I don't know why it works only with very simple scenes, but it's at least also generally it works. If the file you want to render is not too difficult. This is actually how it looks. I don't know what's the problem. Is it? And then it says here external, but it didn't render external. What about internal? Yeah, this is how it looks to render internal. This is what I would have expected in other scenes. So maybe, I don't know, it just doesn't like some scenes, whatever. Just looking if I have something else. Need something from Blender. Do I have something here? No. Scenes, Moment. Mitsuba, Scenes. Oh, here are some Scenes, but none of these is from Blender. So let's see what we have here. I don't think he will render this, but I will try. So cycles render, and then we say Mitsuba. He really started to render this. Okay, so this says it's not all impossible to render something using Mitsuba. So you see something happens. But that's all. More is not going to happen. Maybe he doesn't like the lights in this testing scene. So what else? What else do we have? This maybe. Set it to Mitsuba. And nothing happens. External. It doesn't seems not to render something external. Also at this moment. Internal. So I need the image editor. So this is the result. So this is what he rendered. It doesn't look bad. Also, okay, it does not have a material, but you see he renders nicely. So I imagine if you have something that is, let's try with the external program. Yeah, it's coming, look. Here is it. So if you have something and is made with Mitsuba, he possibly will render it, as you can see here. He renders it nice and fast. You can move it, you can zoom into, and he will still render and refine it as a nice thing. I can even rotate the scene in the renderer and then zoom there. So if you have something that is made with Mitsuba, it looks like this is going to work somehow. So I will try something. I will take this thing here, go on Material, here is it. And okay, I don't see here material. I say add Mitsuba node. And what materials does it give me? Okay, here are some materials. So I have no idea what exactly could be glass here. This looks rather strange. Maybe if we make it a bit transparent. Okay. IOR liquids. Just something. Oh, this looks rather dark. Okay, how does it render? Now something comes. This looks like it's OpenCL. I press play, and now he renders it, and in this case it's dark. So you see, generally Mitsuba also works from Blender, not with all scenes. Also he is a bit, also he doesn't render everything as it looks, but he renders. So for the end I will show you this thing here in cycle, so you see how it originally looked. So, hier noch zum Schluss ein Blick auf die Szene hier mit Cycles gerendert. Sieht sehr hübsch aus hier, bisschen auch mit einer kleinen Lichtbrechung, allerdings hier auch nur mit 25 Samples per Pixel. Deswegen auch noch etwas gestört. Hier auch nochmal ein Blick auf die Szene, die wir vorher hatten mit Luxrender. It looks like this. Render engine, and we want to take a look on the settings to speed up the Blender Cycles rendering engine, and also what points are important to get the most out of it. At first we will take a look on the CPU rendering, but then later we will also take a look on the GPU rendering, because CPU rendering is more and more outdated and will sooner or longer, you can forget it, because the GPU is much faster, and we will also see this later. I have a testing scene here that is a rather complicated scene, and now we want just check some buttons and see what will happen about the rendering speed if we change at these places. So the first thing we want to change is the sampling here. The setting at render sampling is the number of samplings of calculations Cycle does for any pixel in the picture, and the more calculations, the more accurate the result. So we start with a very bad result but a very fast result, and that is sample number 1. So we sample only one time per pixel, and I press F12, and here on the left corner we see the result. Also we get, I can retry, 189, 194, so we are at 190 with the result. And this is how the dragon looks with one sample. So I write this down with the CPU rendering, and these are 12 CPU cores. We get a result of 190. So now I increase the number of samples to 2, and again start the rendering. So we see it's visually already a little bit slower, therefore the picture gets more nice, and we are getting with, I have set it on 3 samples. I want 2 samples this time, so again, and we get with 2 samples about 275 here. I can restart this. So, and now I set it really on 3 and press F12, and with 3 we go up to 443 around, yeah, 430. I do it once more. Also these are 4 seconds, 4 seconds and not even a half second. So we can say 440 is the result of 3 samples per picture, and I set it to 4. We make 4 samples per picture. We get even better quality now, but we see visually is already remarkably slower. We have now used 6 seconds 30. I do that again. So 6 seconds 38. I write down 6 seconds 40. That may be somehow accurate. And we go up to 5. Sampling. So, and here it starts to get slow. We have 9 seconds 35 at the first try. I do it again. Also, let's say it's 9 seconds 50. I write this down. 5 samples. We get to 9 and 50. So I will go on a little bit higher. I will go to 6 now. Not 7, 6. And press F12. Let's see what happens. So now it's getting interesting. It needed 13 seconds plus 2 if I restart it. We are at 12 seconds 35. Also I write down 6 and we get 12:35. So if we are going to take a look here on the results until now, in the moment it looks like we add, with any sample we add, about around the number of what he needs for 2 samples, also so roughly 3 seconds. We will now go a little bit higher and see if this really works. I will now overjump the 7 and make the 8 samples and press F12. So we have it, and it needed 17.87. Also with 8 samples we have 17.87. So now we are going to make a calculation to roughly assign the rendering time of 24 samples. So what we said is, we assume that we get a base time plus 24 times roughly this. I say 3. So I say 24 times 3. 24 times 3 is 72. And we have a base time, so I say I think we will go up to roughly 75 when rendering with 24 samples. Okay, let's try where we get. Here 24. And by the way, watch the picture, it's still a little bit rough, so we'll see how it is with 24. Let's press F12. So we are at the end here, and we needed a lot more than expected, so we needed 2 minutes 31 seconds. So I will write this down, 2 minutes 31 and 68. This means a simple calculation doesn't bring us really to the point how long a picture takes. But now let me make a calculation in seconds and say these are these are 152 seconds, and if I now take the 2 samples value, 2.75, let's say it's 3. Now I make 153 durch 3000. So this is around 51 times the result of what we got here at this place. So what I will try now, I will now increase the resolution and then we see if this will still be true. So I increase the resolution, and this time I increase the resolution by 5. This means we have here 3200 and we have here 2400. So the first thing we do is we render it with 2 samples, and this means I make a 2 here. And let's go. There is one thing that we see here when we render 2 samples only, and that is that the CPU here is not going up to 100%. And so before we go on, I want us to optimize this a bit. When we render not much samples and the CPU is not going up to 100%, then we can optimize to get the same thing rendered faster. We have now a time of 1:22:53. I will write this down, but we did not use all CPU power that we have because it was only till here. So the easier way to optimize this is what we do now, is we do not make auto tile size, but in this case, and just in this case, we are going to increase the tile size of the CPU. Let's say we try 512. F12. So I think we can even visually see that this is going to be much faster. I don't even need to stop the video. It will soon be ready, and the point is we see the CPU is now at 100%, and when rendering with the CPU, this is what we want. We want 100%. Only if we get 100%, our numbers that we have are accurate. Does that mean that a larger tile size automatically speed up our render? No, that doesn't mean. We will see that later. But in this case, when the CPU is not on 100%, we need to increase the tile size. For this time, by using all our power we got with 2 samples, a time of 39 seconds. Also, if we compare this, it's 39:87. It's much faster. And this is normal because we just used more calculation power. We are not at 50% here, but we are at 100%. And this is the number, which we can calculate with. So the next step is we increase the tile size, we increase the sample rate now, and look what happens. Sampling 24 and go. So here we see also while the rendering how the CPU is refining all the tiles. So finally we end up with a rendering time of 1 hour 18 minutes 48 seconds at 24 samples. I will write this down. This is 24 samples and we had 1 hour 18 minutes 48 seconds 40. Also it's twice our assumption from before, but we see that we come here into a region where CPU rendering really takes a while. We will now do the same and not use the CPU, just leave all the settings as they are and render the same picture with the GPU, that means the graphics card. Let's see how long this takes. I press F12 and I write it here. GPU double point 24 samples. Let's see. While the GPU, the graphics processor, is rendering in Blender, we see two things. First, the CPU usage is relatively low. Also from the 12 cores here, only 2 CPUs are really used. The rest is not used. This means the CPU can be used for something else. You can type or surf or do anything with the computer. What you can't do is, if you like to play games, this is not going to work. So for example, if you play 3-dimensional games that also use the GPU, this is not going to work. You can type and do internet, but you shouldn't try to play while the GPU is rendering, because this the GPU now is in usage. There is one more thing we can discuss actually when we see the rendering. So at the moment I would say that we are a little bit beside half of the picture and we have used 13 minutes. So I expect us to have the full picture at around half of the time than we had before with the CPU. We will see that later. So the point is that if you render a picture and it takes 3 hours, how much does it cost? Because you can calculate the graphics card that is now rendering has a peak power consumption of 375 watt per hour, and let's say the CPU is also a little bit used, so we can easily say it's 400 or even 500 total. So if we say, okay, the CPU is used also, and there are components like the hard disk, they also need a little bit, 500 is okay. And that's why you also need at least 650 watt power supply in the computer. But if you have two of these graphic cards, I have tried with 850 and it didn't work, it was too weak. So I have now added 1200 power supply, but I will soon add another HD 7090 990 graphic cards, and at the moment I think we can calculate with 500 watts. So let's say it's 500. In Germany you pay about 0,27 Euro per 1 kWh. This means if the computer generates a picture and it needs 2 hours using GPU, you will need 0,27 times 2 is okay, also is around €1. This means you pay €1 in electricity costs for a GPU rendered picture that takes 2 hours. If you have one graphic card, HD 7900, also my graphic card that I actually have. If you take two, of course, the rendering time decreases by half around. Then you have, let's say, we are talking about 800. And you can nearly say it's 0,25 Euro per hour electricity cost. Moment. Ja, genau. So, that's it. We have here 1 kilowatt exactly. So, no, the real number is 4 hours is 1, Moment, 500, ja, ja genau, okay, also this is it. If we render 1 hour, with this we get to pay this price for the electricity per hour. So, and this is something we will have more in the future. In the past we just thought in how long does it render. In the future we will more often hear how much power does it need to render. So at the end we come up to this question: how much power does my picture need to render until it's rendered? And if it renders 10 hours on 2 GPUs, the cost for the picture is €2.70 about. Also with electricity you can maybe say it's €3. So this is something you can also take into account while you render pictures in the future using the CPU. Is it much better with the CPU? So I calculate that the CPU subsystem, when it's fully loaded here, will also need about 300 watts. So 275 with 300 watts, and it uses twice the time than the graphic card. So if you say I don't use a graphic card, I just use the CPU, it's not really more efficient, because you need the same or nearly the same amount of electrical power, but on the other side you need 2 or 4 times as long to get the picture. And seen from that standpoint, the GPU is definitely the better choice. So we have now the last 2 tiles to render, and here is the last tile to render. If you have a double GPU, it's always good to have a little bit smaller parts so they end at the same time. But now what is the result? The result is we have needed 27, 31, 98. But is this really the result? We are only twice as fast with the GPU. Okay, I will tell you something. We are also talking about optimizations. We have here under the performance settings the option from auto tile size, and I believe this is the automatic tile size that the Blender was setting, possibly for me, or it was left over from tests before. So what I will do now, I will now change this to, remember our picture is 3200 times 2400. So what I do is I will just take half of the picture, that's 1600, 1500, 600. So, and write it here. And this means the GPU will now have a larger block, a much larger block. So at the end we have only 2 times 2 parts to render. And this is, let's see how long this will take. That's interesting. We get in this case nearly the same time. I write it here. 26, 32 und 29. And I make here, we had tiling of 1600. So the tiling does influence the render speed when we have a lower sampling rate. Now the question is, if I make another tiling, if I can influence this somehow. So I will make 3200. Now I get a warning because the tiles are larger than the number of threads, and I make this here, so he will definitely calculate it and split it in 2 tiles, 2 times 1 tiles, and we will see how fast this renders. So we see we have 2 large tiles rendering with the CPU. The result is in this case equal. We have 26 minutes and 29 seconds. Also we were just a little bit faster, but this is really not so much. Also 29, a few seconds faster. So what if we go into the opposite direction, and if we choose a smaller tile size, for example 128, it's a lot smaller. So what we see now is this time we needed a lot more time with a tile size of 128. So we get a rule for GPU rendering, and this is that a larger tile size is mostly much faster. And this is generally the case. While I have experienced that you can set a tile size that is larger than the graphics memory on your card, and then it doesn't render. It looks like it renders, but no picture appears, and you get an error message that he cannot allocate the memory from the OpenCL driver. So let me note the result. We had 53 minutes. So in this case, if we take a very small tile size for GPU rendering, in this case, you nearly get to the time from the CPU, also 53 minutes and 31 seconds. And that was with 128. Now, if you look the difference between 128 and 250, you see the point, and this is also the point here. The longer the renderer is busy rendering inside the sampling, also inside one tile, the better the total result. So what we see here is we have nearly the same result here and here. And the reason is that we had 2 tiles and 4 tiles here, 2 tiles here and 4 tiles here, so there was no large time difference for one switch. So, and here 27 wasn't so much more, even though there were some switches, it was not so much. So now I want to show you the tile size in GPU rendering, also the dependence of the speed from rendering tile size. And for this, to show this, I will go down here, let's say to 2, or let me say to 1. Let me see how fast this renders. If I make F12, so with a tile size from 1, what I say, with we have the same picture size, and we have now samples 1. Here we had samples 24, and now samples 1, and let's see, we get mit 128, 128, we get a time of, and this shows very easy the thing. Also we have 45 seconds, 54. Ich schreibe mal 45, 54. So, and now I'm going to increase the tile size, and we will just see what happens. So 256 next. So 11. So you see again the jump from 128 to 256 is remarkable. At 256 we are now at 11 seconds. So it's a third. But we won't stop here. We go to 512. And what happens here is, and this effect is getting stronger the larger the resolution of the final picture is. We are now at 7, so 512, and we are now at 07, Doppelpunkt 86. So the point is that what we do now, I go to 1024 and press F12. The point is that in this sampling area, the renderer is not long time inside one tile. So the most of the time goes for the tile switching work. And this work is what makes the rendering with GPUs slower. This means the more samples we do, the longer we are in each tile, the less is the part of the switching overhead. Of course, the switching overhead is also smaller if we use larger tiles. And that's why we get 865. Oh, this time we got slower again. Look, 0865. Okay, I want to see if this stays if I press F12 again. 804. Also, so now I go back to 512. I want to see if this is anytime faster. 810. So this time, do it again. $765 even, also even faster. Also 512 is here, looks like it's even faster than a larger tile of 1024. This is resolution dependent. If I take a much higher resolution, larger tiles become more efficient. I will now try larger tile size, for example, the 3200. Oh, this we have the fastest time. You see, 3200. No tile switching, because we rendered all tiles immediately. We come to 06 and 95. So this is how it looks. Tile size 128, very slow. Default tile size 250, 11. And if we manually set the tile size large size, we get nearly the half time. So let me see how far. No, I think this is the maximum. I can theoretically set a larger tile, but he will make it even smaller to get 2 tiles out of this. So we can try 1600. Then we have 4 tiles. 1, 2, 3, 4. And the time is 724. Also is here inside 1600. And then we are with 0724. Also it's faster even as the 512. This means here the larger tile size is better. I don't know why the 1024 runs out of the row. Let's take a look. $842. Yeah, that is just a little bit slower. Okay. So what doesn't make any sense is to take the very small tile sizes. For example, 60 doesn't make any sense for the CPU, but just for fun, I will show you what happens if you take very small tile sizes with the GPU. So you see, it starts here rendering, and it takes time. doesn't get really forward. We are already, we not even have the half picture and are already over 20 seconds. Also this doesn't make sense, so I stop this now. And even 64 doesn't make sense. We can try. So we are already over the time we had for 256. We are already on 20 seconds, so we will end up here with a render size of over 30 seconds or nearly 1 minute. So we must not wait to see the rest. And then, as said, 512, we do it once more. 512 is the first good result we get here. 824. Okay, maybe this was really a little bit low, so I do it one more time. 771, also even faster. We have here 771. Also with 512, somehow we get a good result here with one sample. And this was with samples 1. And now, what I want to do now is I make samples 2, and we will check if we get the same result. Also if we get a better result here and a worse result here. So for this, I will change now the samples to 2. And we see 4, no, 2. So, and we will see how the rendering with the GPU and different tile sizes will be influenced. We have now that the renderer is longer in each tile. This means the effect of the tile switching will be a bit less. So let's see what this makes practically. We start again with 128. Oh, this will take a while. So this is really funny. We get 36 seconds 29, and this is less than we had above with one sample. I will write this down. 36 seconds 29. And I want to verify this. I will now go back and make it on one sample and see if the result really stays. That is faster with 2 samples. No, there really is, also with 128 samples 1, we come to 19. That is real. That is the real result. So 19, 29. So this makes sense. So okay, we have 36, 29 with 2 samples. Now if we compare with the time with 1 sample, if we would take this times 2, we come to 38. So we have nearly the double time. Then so if I say we had 11 with 256, I expect we could go here. Moment, 2, 2. We would be here with 256, possibly around 23. But let's see. We will check that if it really works like this. 256 tile size and render. So not even 23. Also we are nearly even less than double. We come to 1946. 1946 with 200. 56. And now I want to try this again and make a change here. We have seen that the rendering starts in the middle and goes in a circle around, and now I say we make top to bottom, for example. So now after this change, the renderer goes here from left to right and up to down. So let's see if we get the same time or another time. 1949. Also this is, let's say, the same time. It doesn't make a difference here. I want to try another one also. I say we make right to left. This is from this side to this side. Does it make any sense? So this was faster. Take a look. Not much, also a second maybe on 22nd, but it looked faster. 1904. So from right to left, at least wasn't worse. So what is left to right? Oh, this was the fastest, 1893, also left to right looks like to be definitely faster than the center thing. 1893. Okay, also left to right seems to be possibly better than the center thing. We try one more, the center thing. 1950, definitely 1946 was okay. And so I go again to the left to right. Okay, this time we got 1946. This time we didn't have a large difference. Also let's say the left to right and center doesn't make really a difference, so we leave that and we continue with 512. We end up with 1467. So we saved 5 seconds. And we go to the next tile size, 1024. Oh, that's interesting. Again, with 1024, we are a bit slower here. So again, we here have some sort of penalty, and we come to so let's try the next one, which is 1600. So we have 4 tiles, 1, 2, 3, 4. Und bam, we have 1423. And I believe this will be around our maximum time. Also we can't get much better here. We have again the 3200, which only makes 2 tiles in this case. And we expect here to maybe go to 1 second less. Oh, 1511. Also in this case, we didn't win much. Not 12, 15. So these are the actual results. The best result was 4 tiles, 1600. And 512 was also okay, was a good result. But I want to make the 3200 once more, if we have tolerance here. $14,70. Also we have here again nearly the same value, 3200, like we have with the 512. Even the 512 in this case was a little bit stronger, don't know why. So we saw that there is a slight difference about one sample and two samples. And now we go to sample 8. Also we make the same with 8 samples again and look how this will influence the process. So this time we start with 3200 and we make samples 8 and go. So, das erste Ergebnis haben wir und mit 3200 ist es 03, 04, 00. Naja, 42. Das ist eh unter einer Sekunde, spielt da keine Rolle. So, und jetzt gehen wir einfach mal runter auf 1600. Schauen mal, wie sich das entwickelt. Was wir auch sehen, wenn wir mit der GPU rendern, ist, dass, wie schon gesagt, die CPU kaum belastet wird. Also von den 12 Cores hier, ein Core hat ungefähr 8%, also 100% sind alle 12, haben wir hier eine Auslastung von gerade mal etwa 2 bis 3 Cores für alle Programme, die da jetzt gleichzeitig laufen. Und was das im Detail ist, kann man auch sehen. Das ist alles möglich, zum Beispiel der Search Indexer, aber eigentlich kaum. Also Blender verwendet die CPU kaum. So, da liegt auch schon das Ergebnis vor. 3 Minuten 19, erwartungsgemäß. Oder auch nicht, waren wir hier jetzt ein klein wenig langsamer, aber wir sind auch um diese Zeit rum. Also da kann durchaus auch eine Messtoleranz drin sein. 3 Minuten 19, je nachdem, was jetzt Search Indexer und andere Programme, die da noch so auf dem Rechner nebenher laufen, noch alles tun. Jetzt schauen wir mal bei 1024, was sich da ergibt. So, we have the result. It's 3 minutes 14. And this is for now the best result. 50. And we come to 512, which was one of our favorites in the last tests. Let's see if this is here also the case. And let me say one thing. due to the way how GPUs work. Can I have a picture for this? Let me see. Do we have a picture for GPUs? So due to the way how GPUs work, this is not a result that can be taken one-to-one to any graphics card. It's more or less a result that depends between the resolution, the tile size, the number of samples and the graphics card. So with time and a little bit trying, you will get a feeling for what the best tile size for each sample number on your GPU is. No, it doesn't show me this. Do we have something else here? Okay. Here's something. Yeah, this shows it a little bit. Here, imagine the following happens internally in the GPU. We have here the wavefront scheduler, and here are all the steps from the program, and they are executed in several computing devices. Also 0 to 19 in this case, but it can be also 40. I think it's 40 such also several devices who execute this one by one at the same time. They are not really fast, but they work all at the same time. So we have the best result with 512. Look, it's 2, 0 to 58, 77. So it's the best result from the results until now. And what we expect is that we now with 128 get a much worse result, and that's the next that we try. 100, now I will try next 256 of course. And go. So we got as a result 3 minutes and 10 seconds. So this is a worse result. So 512 is also here for this scene and this graphic card maybe the best settings what we see. So for all cases I will try the 128, but what we expect is that the result will be much worse. So this picture shows graphically the difference between a CPU and a GPU. So what we see is that the CPU is faster but has much less cores that execute at the same time than a GPU. So this means GPUs have slower cores with less abilities and less caches and a lot more of these. And CPU has 4, or in our case 12 cores, and is effectively on parallel on jobs that can be parallelized much slower because the GPU renders with 500 and more cores. We see here another thing about the paradigm shift. because actually the manufacturers of computing devices have run against a wall, and this wall is the frequency of the devices. They cannot make more gigahertz, they cannot make higher frequency because it's physically, technically not more possible to handle higher frequencies, so they're working things in parallel. They make many things at the same time, and this is the way out, the way around this this wall, this gigahertz wall they have been running against. More transistors need higher frequency needs higher power consumption, and this was the clock speed race, and 4 gigahertz was the limit, and they run against it, and now we have the multi-core evolution. This is the next step, and multi-core evolution means we are doing many things at the same time instead of trying to do one thing even faster and faster, because this is not more easily possible. So under some circumstances we can continue with Moore's law to some degree if we use multi-core. And multi-core can be CPU, but multi-core optimized is more the GPGPU. This is the graphic processing unit. A graphics card has much more cores than a normal CPU. As I said before, it can have 512 or more cores. Unlike a normal CPU, next year we will get one with 20 cores, which is not so much. But these cores are optimized for fast serial processing, and are of course much faster than the cores on the graphics card, but the graphics card has much more cores. Personal supercomputing is possible if we use our graphics cards for jobs that can be calculated in parallel tasks. This picture here shows it a little bit. Serial computing on CPU and parallel computing on GPU. And this picture shows why the GPU is faster, because one of these execution units is slower than one CPU execution unit. But they all work at the same time, and this makes the throughput very large. So our rendering comes to the end, and as expected we are very slow. 6 minutes 12 seconds is the result, and this means we have used twice the time that we have used with a better tile setting. 6 minutes and 12. So also we see here that 512 is with samples 8 the best value, and we see that with samples 2 it's the best value, and with samples 24 it's also at least a good choice, while 1600 may be a better choice for higher value samples. So just for fun, did we render this with the CPU already? This has a resolution of 3200, 2400, So just for fun, we will render it with the CPU. And how many samples do we have? 8 samples. No, that's too much. 8 samples. This will take a lot of time. And let me make an estimation. Also it will half an hour maybe. Okay, and what tile size would we take for the CPU? Best 1024. Samples 1. Okay, about rendering with the CPU, let's make a try. So I go a little bit down and make here samples 2, 4. That is, so we will see the result. So samples 4. We take again and come back to the rendering with the CPU. Before we do that, we render this now with the GPU, and we make our base setting. That was normally 512, so we can just take it from here and see the result with samples 4. That will be here in between, samples 4, and CPU tile size is, no, this is GPU, tile size is 512, so this is our value that we need, that we compare the things that we get with the CPU in the next test. So we already have the result, and the GPU needed 54 seconds and 69. And now we switch to the CPU and we choose a tile size of, let's start with, so let me first switch to the CPU. And we take the same tile size, also we take the 512. So no change, tile size 512, take the CPU, let's see the difference. So what we see here is that in this case that we have 4 samples, we have a high degree of CPU load. This means we are on 100%, and this is a good sign, because if we are on 100%, normally the result that we get is really good. Also we will not get far above that. We will not get a much better result with another tile size, I think. So, but we will see this in the further tests. So soon we have the result. Only 2 cores already running, 1 core running. So, and we have the result, and it's 2 minutes 20 seconds. 512. We get here 2 minutes 20 seconds. So here we see that we need twice the speed, even with 12 CPU cores, than if we have a good graphics card at the same tile size. Now let's see if we can get better results with the CPU, but I doubt that, as I said before, because we have had 100% in the task manager, so I think we will get less. I will make a try. I will now make a very small tile size of 16, also really small tile size, and we will try that and just see what happens. So what we see is the very small tile size leads to that he quickly paints, but in the task manager we see that we have no 100% CPU usage, but we are just at about 60, 70% around, 70 to 80, but not 100%. So this will definitely take, let's say, 20% at least longer than the one before. So here is the result. CPU with tile size 16. We are at 3 minutes and 37 seconds. And what we have seen is that the CPU usage was not 100%. And there is one thing that I really wonder about, because normally I could then, for example, try and increase the number of threads. For example, I could say I have 12 cores. So if I don't get to 100%, I could, for example, say I make 24 or 26 threads or 28. So even I can make 64 threads, and this is what makes me wonder that I don't get the CPU usage to 100% with Blender. So I expect something to be wrong in the program about this, because if I make a lot of threads, I should get CPU usage up on 100%. So I will leave the 16, the tile size, and I have now doubled the number of threads to higher than the number of CPU cores. So each core has now 2 threads, and if I had before 1 thread per CPU core going up to 80, 90, I should now be on 100%. You will see that if I press F12. And so we see it's the same like before. So we don't get the CPU to 100%, not even with 32 threads. And this is really wonders me. Then I will now stop the rendering and make this to 64. That is the highest number of threads I can make. And if I press now F12, let's see what we get. And again, we get between 60, 50, but we don't get the CPU up to 100%, and this is really strange. Also, I wonder a bit. It looks like the scheduler who gives the course, the job, seems to be not fast enough or something. Also, I would expect here to get 100% CPU usage with 64 threads. Is not the case. So I expect, because we have the same CPU usage, even with 64 threads, the same result like before. And as said, this looks a bit strange to me. Maybe there is something not yet perfectly done inside Blender about threads. I should get CPU usage here up to 100%, I think. So let's see what the result is. So the result is, as expected, 3:36:28. Also 3:36. So I wonder about this really. Normally we should have a different result with 64 threads, especially we should have more CPU usage. So we will take a look on this later. And we go now and we make it from the other side. I will now make a tile size of 1024. I will leave the thread number on 64. No, that doesn't make sense. Okay, we go to 256 is the maximum. With this thread number, 256 is the maximum. Let's see what we get with 64 threads, and then we will go back to the 12 threads, which is normal. And let's see what happens. 256, and we had 64 threads. And so this is what we see here. Each thread renders one tile, and these are the 64 threads, so it's nearly half the picture is rendered here at the same time with a thread. And from my subjective view, I would say this is going to be faster. And also, if we take a look into manage, that we are 100% a good sign, because if we render with this and we are always on 100. We are near the maximum power. We use the full power of the CPU, so we will not get much better with any change setting about CPU tiling, if this is the case, and this is the case here. So, as expected, we see that the tiles that are over the dragon figure are those who need the longest rendering times and are those who are left at the end. Of course, when we have tiles left at the end, the CPU usage goes down, and this is the part of where we are less efficient for a bit. So in at all, we got now 2 minutes 12 seconds. Also this is our best result until now, 2 minutes 12 seconds. And what we will do now, I will now just reduce the number of threads to 12, which is the default value, is 1 thread per CPU, and we will see if we get the same result or not. So what we see here is that with a tile size of 256 and 4 samples, we get a CPU usage of 100%, and this means that we will be around the same result, I think, because this is the CPU power that we have to sample all the pixels with the amount of 4 samples. And this is the maximum power is used, so we will get around the same result. This is what I think. There will not be a large difference. But let's see what we experience at the end. What we see here is that we have not so much tiles at the end left on the dragon. Also just 2, 1, and they are all together ready, so our result is 219. Also we needed a little bit more time. This means using more threads was more efficient. 219. Also the best result is 256, 64 threads at the moment. So we don't know if 64 threads is the best. Maybe 32 threads is better. We didn't check this. But let's first try 512. I want to change the tile size, 512. I leave now 12 threads, and then later we make more threads. So again here we see that some tiles on the dragon are left at the end, and we see the task manager going down below 100%, and this is the time when we are not perfectly efficient. So we will see how this is going to influence the total result. This is the result. We have 220. 0,220. So this is our result up until now. So the best was 256 and 64 tiles. What was this? 2 times the same. Okay. So now what do we change? Also we have 512. Now I will just increase the number of threads. Let's see, how many can we take? 32 is okay. Can we take 64 even? No, 64 is too much. You see here the running. If we take 64, then one CPU will not be used. So what about if we take 63? 62? No. Okay. 50? 40 is even too much. Okay, also we stick with 32. 32 works, and let's see how this influences the result. Also we have CPU 512 and it's 32 threads, and we get, so what we see is with 32 threads that nearly the whole picture is rendered at the same time. 33, 34, 35. If I would have taken 35 threads, the full picture is rendered at, I think I will try this next. 36 is too much. 35. Of this system is that we have at the end a time where we are not very efficient. This means we have the 100% most over the time in the task manager, but at the end, when there are some threads, those over the dragon in fact are left over, then, and this is happening now, we lose efficiency, and we see this here. The last time we are rendering not so efficient because we have these threads here left rendering the difficult parts and the easy parts are already done, and then we have this time which is not so efficient at the end. So I expect a worse result, but we'll see. So now we have 220 and we are ready. Also we have 225. So the result is a little bit worse as expected from before. It's now I will try with 35 threads. We have the same problem here with 35 threads. All the easy parts of the picture will be ready, and those parts in the middle with the dragon will be left over, and this is just a problem. Then we will have some time here where we'll be terribly inefficient, and this is why we will not get a better result here. And I guess even this tile that came last here is the one that will stay longest. So again, we have exactly this difficult process here left, and this is the reason why we are here over our time. It's gone to 22. Okay, but we have a little bit better than before. It's a good time. So we can build on this. So what I try now is I try the larger tile size, and then I have of course to reduce the threads to, let's say, 24. 24, 27 is also possible, and 30. No, 30 doesn't work. 27 was also too much. Yes. We need 24. 24 is the best value. We see that here, 6 times 4, 24. So we make 24 threads, and then we render again the complete picture at once. The Blender will automatically adapt the tile size a little bit. That's what he says here. Let's see how much we get. So here we see that the whole picture renders at once, and we get immediately a CPU usage of 100%. Always the problem is that this part and these parts will, especially this part, be a little bit difficult at the end as it looks. And will bring us this time where we are not rendering very efficient. So we already see that we're running here below 100%, and this is the disadvantage of having large tiles. If we have smaller tiles, all CPUs can render until the last moment. The larger the tiles, the higher the chance that one CPU or less is alone rendering at the end and is decreasing our effectivity in rendering. So this part here is left, and one CPU renders all of this, and this is increasing our rendering time, and that's why we are going to try smaller tile size next here. But first let's write down the result. That is CPU and we have 1024 with 24 threads, and the result is 0245. So it's even worse. So we go the other direction and try tile size 200 with 64 threads. So here we make 64 and we try a custom tile size of 200 and then next 256. But let's try this one first. This time we render from right to left. What we see is that the CPU usage is very high. Also we are at time, and that's a good, we will possibly get a good result here when it's ready. And now the advantage of the smaller tiles is that we don't have a large tile at the end left, which is rendered by just one CPU, but the same tile is rendered by, for example, 5 CPUs. So what we see is that we have with smaller tiles 100% efficiency nearly all the time, and this is why we got a very good time. Is 1 minute 51 is the result, and this is the best result. 1 minute 51, and this is the result because we have a high efficiency here. So with CPU 12 core, this 200 looks really good with 64 threads. Now I want to try what happens if I make 300 instead of 200, and then later we try the same with 128, for example. So CPU 364 threads. So we are coming to the end here, and 300 is a larger tile size. Again, we have here a little bit inefficiency at the end. Okay, but we have the result. It's 153. So this is nearly as good. 1,53. So now I wonder that with 256 we had this result. I want to verify this. Maybe this was not, I write it wrong or something. So, and go. Maybe this is not real. So we are getting to the end again. We see here the efficiency is going down slowly, but at least we have 4 CPUs ending until the end, so it's still a good curve, and the result is 154. Yeah, this is expected. This is expected. So 200 was actually the best result. So let's try with 128 and 64 threads. What do we get? So I will tell you what I expect. So what I expect is that we don't have the inefficiency at the end. But what we see here is, for some technical reasons, I don't know, compared to here, we have at the start not 100% CPU usage. And also here, the curve is not completely straight. So the total CPU usage is now worse. And this, from this standpoint, I would say the result that we get is worse than before. So the advantage of the smaller tile sizes is that we do not have this inefficient end that we had from the larger tile sizes, but we have, if the tile size is too small, and this is what we see here, not the 100% CPU usage over the whole way. And if this appears, you know the tile size is just too small. So the result is 212. Let's see. 212. This is 128 CPU. Here you can see and compare the results. 128 with 64 threads, and we got 212. This is not a really good result. Our best result was 200, so the question is, what is between 128 and 200? Does it get better or does it get worse? So let's try 180. 180 and go. So what we see is at the beginning a little struggle, but then the end is very fast, so we have no inefficiency at the end, and the result is okay. So we get 154 with 180. Also 180, and we had 64 tiles. Threads, of course, and we get 154. And Okay, now I will try to reduce the 64 tiles to the normal, which is 12 tiles, and we see if we get a large difference. Again, we are coming here to the end and the time is 2:11. So this is worse. This is definitely worse. So what we see is a large number of tiles that is higher than the physical number of cores in the CPU is recommended. Otherwise, you will end up with a bad, so a worse result. So what happens if I use too few threads? Also, you know, I have 12 cores. These are 6 cores physical plus 6 hyper-threading cores. What if I render only with the 6 cores? Let's see. So, interesting enough, we get even with 6 cores to 70% CPU usage. Okay, also with 70% we will not get a good result. It's just because of this I must not go on. So what I try is, if I take not 6 but 9 or 10, so not 12 but 10, and now let's see what happens. Okay, now we come to 93, 90, 92, 94. So we don't really reach the 100% CPU usage. We can stop here. If I make 11, so this would mean we have 11 threads for rendering and 1 thread for anything else. 1 CPU reserved for something else, and now we are going to 98, 97. So let's see what we get. So this time we are not really on 100%, but we have 2% left. So what is good for example, if you want to write something, edit something, and while it's rendering do something else, you can keep a little bit CPU power for yourself, and this is what you will do in this case. You will take the number of threads it will give you automatically and take 1 CPU out for yourself. Then you can work, write, or do something else, no games anyway. And then it will render in the background and use all other CPUs that you don't use. And this is what you see if I move the notepad, for example. We come here really to up until 90% if I do something else aside. Right from the mathematical side, 8%, 8.3% is 1 CPU. So we see that the last CPU we don't use for rendering here is used by something, whether it's the system services or Windows itself or something anyhow is using the CPU, and that's why we come up to 99% here. So this was it, and we have 2 minutes 22 as a result with 11 threads, and this was expected. So it's worse result because we didn't use all our CPUs for rendering. But as said before, it is recommended to use more threads than you have CPUs. For some reason, this is an advantage with Blender. Okay, possibly these rendering threads call a subprogram that's called do events, and this enables Blender to react on UI events. And if this is called for a longer time, then this result would be explained. Okay, what we try is, I want to try 32 threads before we switch to another tile size and try another tile size. So here you can see the results so far. We have with 4 samples, and of course the GPU version is still twice as fast as the fastest rendering with the CPU. But the CPU comes closer than I thought. Well, okay, it's a 12-core CPU. Now we have with 32 threads, we have 153. Also this is nearly, no, this is definitely the best result until now with 32 threads. So the question is if 32 is the best number or if 24 is better, and we will try this next. And we have the result with 24 threads, which is possibly somewhere in behind here. So 180 and 24 threads, and we get 0, 2, 0, 2. So this is not as good as 32 threads and not as good as 64, but is better than 128. So what was the best result until now? Still 264 threads. So what I will try now is 232 threads, and then we are done with the first test series. Also 200 tile size and 32 threads. Let's see what we get. Sharp and good CPU usage at the 100% line, and from this we already see that we will get a very good result. And we will see at the end, because it's not so large tile size, that we will hopefully also have a sharp curve at the end, and this means we have a very good efficient over the whole calculation time. So this was it. We have a very sharp edge at the end here, so perfect curve, we must have a good result. It's 155, and now we can make a conclusion. Also, rendering with the CPU depends a bit on the number of samples. So we had different examples depending on the number of samples, but for example with 4 samples we had with a 12-core CPU at least a better result if we take 64 threads. This is the maximum number of threads we can take, and in this case with this rendering we were good with this resolution, I have to say, with a tile size of 200. I must say that I had pictures where a tile size of 16 was really good. And to see how dependent we are from the type of the picture, we will now switch to a completely other picture and do another series of tests. Okay, here we have the famous BMW benchmark Szene, and now we want to use this for our testings. In this time we will take a larger dimension of 7000 by 3500. But then to go quickly forward, we will now use a very low sampling rate of 1 for the starting. Just 1. And try different CPU and GPU settings and see the results. So, but what I do first is I will set this window to an UV image editor, and then we can set this window into a property. Yeah, property we have already. We'll make it to a node editor where we see the material. So sample rate is, we have set it on CPU. I think the experimental is, but this doesn't matter at this place. So CPU and sampling rate is 1 here. And now the performance settings here. We have 12 threads and a tile size of 128, and this is, I believe, too much, but this is what we are going to see. This is just another thing here. We are now going to find out what's the best value to render this. But I want to start here. Remember, we have now a larger thing. We have now 7000 by 3500. So first what I do is we render it one time with the CPU. So we have a value how much the CPU will use for this. And for the CPU we have always had 512 was a good value. And CPU threads, it doesn't matter with the CPU. How much does he give me? 64? So when rendering with the CPU, threads should not matter. But let's just see what we get. So when rendering with the GPU, as always, the CPU usage is low. And the Blender says he's at the moment loading the render kernel, and this may take a few minutes the first time he renders the scene. So this may take a moment before he even starts to render, and this is now. And then we see he has now started and is starting to draw the image. So this is the result, and it's ready. He does some sort of post-processing, and here the CPU is used, as we can see. So this is in progress. He will do something so the lights get shining and such stuff. This will be the same with any picture, but this does not help us with our test. Maybe I can disable this. So as we can see in the post-processing, he has made a little bit with the lights and this. Let me see here. I will disable this post-processing thing, because otherwise we don't get accurate numbers. So I will render this again without post-processing. So we are near at the result. And the result is CPU is down, picture is ready, 1:16:45, 1:16:45, one sample rendered with the GPU. So this time I also want to try a larger tile size for the CPU as we did before and see if it makes a change. So this is ready. And what is the result? It's a bit faster. We come here to 59 seconds. So we see this is a difference. This is definitely faster, 59 seconds, or let's say 1 minute, but it's over 16 seconds faster. So we can even push this a little bit higher. Possibly 3500 is still working. So now we have only 2 tiles, and of course we have one problem. If one tile is faster ready than the second tile, then we have one time where only one of the 2 GPUs is working, and we have a time where it's inefficient. If both parts are roughly ready at the same time, we may have a slight advantage in numbers. The task manager, however, will not help us at all. So what we see here is that the left side of the picture is faster to render and that the right side is not yet ready, and this means we have an inefficiency here on the right side. And what is the result of this? The result is 59:12. Also 59 seconds is as good as before. 59:12. Also this is a large tile size is good for GPUs often in case we have a low sample number. So this is what we see here. And if we compare this, we can definitely see that the large tile size makes things here faster. So okay, we take this 1 minute is the time we need with the CPU, and now we go back to the CPU testing and set it to CPU. Now we look what we can do to get as much as close as possible to good values with adjusting the thread number and the tile size. So we had already been testing. No, we have not. So then we start with, I click auto tile size, I open. What did he do? He don't show me. Okay. Also, let's make a calculation. We have 64 threads. This means 512 is the maximum before he starts calculating. And we have then 14 times 7. That's what he's going to do. Let's try. So this time we are not going from left to right, but this time we're starting in the center and going to the outside. This has the advantage that we do not have the inefficiency that some threads in the middle stay while others at the outside are ready, because they start first in the middle and hopefully they are ready when the CPUs enter the border area. That's the advantage of this circular going to outside. So what we see when we render CPU with low sample numbers is in the task manager that we have long times with low efficiency. And this is what we get, 145. While this is not really a bad result, because we are not much slower than with the GPU, but I think we can get better here if we get the CPU on 100%, and for this we need to increase the tile size, and possibly for this again decrease the thread number, I think to 32, and even then he will take 8 times 4. Okay, let's try. So what we see is he is rendering the whole picture nearly in one run, and what we get is we get a better CPU performance than before, but we are not staying at 100% here. So still we have here a point where we are not efficient, and we need to get around this. Something is not yet efficient in our settings. So what's the result? So now he should be ready. And we get 122. So this is better than before, because we had a better CPU usage, but we are not yet good, and this means we will further decrease the thread number and further increase the tile size. Maybe I go even to 12. But now I increase the tile size and I go to custom and say I want a tile size of 3500. Oh, he doesn't do that. Okay. 4 times 3. No. 1500. Okay, let's try this one. Again, we are rendering nearly the full picture in one run. And let's take a look on the task manager. So the start is good. We are going not so deep like before at the moment. But now we are getting terribly inefficient. So this did not really help much. So after all we got 0, 1, 0, 6. That's the best result until now with 1500, and we had 12 threads, and with this we got 0, 1, 15. So that's our top result at the moment. So how can we beat that? Possibly I can go up to 2000. What's our resolution? Our resolution is, let me take a look. We had 7000 by 3500. So the best would be we have a multiple. if I make 3500, I will try. So we see the start is good. The start is up to 100% CPU usage. This is what we want when we render with the CPU. Then we will get good results. But let's see if it stays like here or if it falls down again. The moment it falls down a little bit, and this is the problem, while we have a good efficiency inside the tiles, we are falling quickly down because we have no more, we have only single threads running at the end. This means we'll see how efficient this will be at the end. This was 3500 and we had 12 threads and we got 116. So this is our second best result, so it's nearly as good as with the 1500. So but we have the same problem here, that maybe we simply need more tiles. So I make a smaller tile size. What can we try? We had 1024. What if we make 1200? And now we make more threads. Let's say we make 64 threads. 64 is too much. Then he renders all together. Make 32 is also too. Let's see, 32. 32 is too much. If we go 1000. Too much. If we take 24 threads, okay, this will work. We try. So let's take a look on the task manager. We go up to 100%. The start is good. He stay up on 100%. Looks good. Okay, from this, what I see in the task manager, I would say this will be the best result we had until now, because we have the longest 100% curve, but now it really drops low. I wonder if a much smaller tile size would give us better result. We will make a test about it. Because we have a large tail with inefficient calculations here. On the other side, if we have large tiles, we easier get it to run to 100%. So now we have 0, 1, 12. And this is our best result until now. So if we take a look here, 1000. How many threads did we have? 24 threads, and we got 0, 1, 21. And this is really near to what we had with the GPU. So it's not much far away from the GPU. So double punct. So while this is not so important. So the question is, where could be the power? Should we go up to direction 1500? Oh, I just see with 1512 tiles we have already beaten the... No, GPU was 0059. Here we are. This was the GPU with too small tile size. So, and with, so this was our best result. It was with 1500 at the moment. Now, let's try a smaller tile number, a really smaller tile number, but we'll see if we can get the threading on. I will try custom. I will try 750 for example, and then we try 64 threads if possible. Oh, that's too much. 64 is too much. Okay, 32. It will work, and go. So we have a good start. As we see, we start with 100% CPU usage. Let's see how long we can stand with this. Okay, it's dropping very early. Oh no, it's dropping down. Why is it dropping down when so much tiles are not yet calculated? Well, this is what happens when you have a very low sample number. Then the CPU rate is dropping low, and I don't know why, because the picture is not yet ready. Now it's going up again a bit. And soon we have the result, and it is 124. So this is not a bad result. It's around here with the 1000. It's a little bit worse. So if we have 750 and 32 threads, we get 1 and 32. So now if we look at the numbers, our best result was 1500, and also good was 3500, because we had the highest time with 100% CPU usage. So what can we do about this? Okay, also from what we see is that even the tile numbers, when we have a low sample settings, is difficult to get the 100% CPU usage. You will see one thing: if I change this to 3, for example, we will have just other conditions, because now the renderer stay much longer inside a single tile, and for this we will have a very good CPU efficiency. But first let me again make the GPU rendering, and we use again the, I think the 3000 200 was the best, or 3500, so we can just leave this and find out what's the point where we do best. 3 samples. GPU Samples 3, GPU 3500 die size, and as a result we have just a left side and a right side. Again, what we see is that one side was a little bit faster ready than the other side, but now we have the result and it's 5 minutes 9 seconds. So GPU, we have 5 minutes 9 seconds, and I don't believe that we will get much better here whatever we do. We can just to try one more time the GPU thing with 512, as we got some good results in the past, but I think we will not get these good results. We will try. So we have the result, and it's 351. Boah, that's much. 359. That's much better than the other result. This time the 512 beat the 3500 easily. So it pays out to try different tile sizes depending on the sampling rate and on the picture. 359. That's a good result. So we take this as the measurement and go to the CPU rendering back. And what was our best result here? With the CPU, the best result was a tile size of 1500. So I will try the tile size of 1500 also with the GPU, just to have a number to compare, and let's see what we get. So this time we land somewhere in between with 4 minutes 18. So I will write this down. 1500, 418 and something. So the 512 is still the winner. And before we go on with the GPU, let's come back to the CPU and look how we can get the best result. Outgoing from the above 1500, what we actually have, should be a good thing. So let's try. We set this to CPU. Now CPU, here is it. And what we do is we make the threads to 64, which is too much. So we make 48. 48 is okay. And go. So what do we expect outgoing from the results at the rendering? We could expect somehow 4 or 5. Okay, let's see. Oh, we have here a row with small tiles. Okay, we will see what happens, but at least what I can say is our CPU curve looks at the moment really promising. Now it goes a little bit down. We're getting a little bit inefficient and it goes up again. That's good. Okay. So the CPU curve looks roughly okay this way. It's not really straight, so could be a little bit better, okay, but we'll see if we can get a better curve when we change the parameters later. So we got the result. Naja, the curve was somehow okay. So what did we get? 6 minutes 16. It's not so bad anyway. It's not half of the GPU. So it was not so bad. 6 minutes 16 and this was with 750 and 48 threads. So what I will do now is I will switch back to the normal 12 threads that you get if you don't change anything. I will leave the tile size just to show you the difference between 12 threads and I say over threading if you make 48 threads or more threads. So from looking at the CPU curve, I would say that the curve is not as good as it was before, but we'll soon see the final result with 12 threads. So we have not changed anything else than just taking 12 threads instead of 48 threads, and the result is that we needed more than 20 seconds more. So it was definitely slower. And this means that I call it overthreading. Makes sense with Blender. I don't know why, but it's like that. It's like that. If you take more threads than you have CPU cores, you get a better render result here. We have seen this now a lot of times. It's not so much, but it's a better result. So overthreading pays out. So looking at the result, we have really good results compared between CPU rendering. Okay, let's say it's 4 minutes, and here we have at the best 6 minutes. So okay, but we can still work on the CPU curve. We can try something. What can we do to get the curve more high? Okay, let's try, for example, a very large tile size for the CPU does not have, because we must at least get 12 threads. So what we can do is we can take the We have 7000 by 3500. We take the lower number, that's the 3500. We divide it by 12 and we get 291. So this is the number that I take for the here for the target size, for the tile size. And now, of course, I do an overthreading as much as I can. I take 64. And let's see what we get. So from the CPU curve, what I see now, it doesn't look like so large advantage. I would say we will need a little bit larger tiles to get the CPU curve more up, possibly. Okay, but we will see. So, let's see what we got. We got 7 minutes and 27, and this is not our best result. So we must not experience this more. Let's see, where do we get better result? Also here with the smaller tile size, we get a worse result. Let me try our good old 512 next with 64 threads possibly. 512 and we have 64 threads and we go. The best number is still a GPU with 4 minutes and 6 minutes 16 with 48 threads, and a size of 750 is until now the best number. What we see here was a good start about the CPU usage, but now let's see if it stays up. If it stays like this, we will get a good result because we are really up here with the CPU. So we have the result. Let's see. It's 639 with 512 and 64 threads. So we have 0639 and this is nearly the same result like we had with 750 and 12 threads. So this looks like we should increase the tile size a bit and yet try to get as much threads as possible. But first I will try with 1024 and take less threads and see what we get. So the start is good. We see the CPU goes up on 100%. So what we see about the CPU curve looks not perfect, but looks rather good at the moment. Let's see how the end comes. So now we see we are losing efficiency here, but we are already at the end. I see 2 threads rendering. And whoops, that was it. We get a result, and this is which result? 559. So this is our best result until now, and we get this with 1024 and 24 threads. Also 1024 and 24 threads. We get 0, 5 and 59 and 64, and this is nearly as good as a bad result of the GPU we had here with 3500, just a part of a minute missing, so 50 seconds. So we see that with a greater tile size we get a better CPU usage. So the question is, how far can we go about this? What is if I go up on 1750, for example? Of course, I must reduce the thread number then. This is the danger about it. Okay, what is about 1500? This could be, so we try. What do we get? So as it looks, we will start with a very good efficiency, but then go soon down, because when the first tiles are ready, we will render the rest with only a part of the CPUs. But let's wait and see what comes out. So, we will see. What we got is 646 with a tile size of 1500. So this is a worse result from what we had before. And it was 12 threads and we got 646. And so the truth is somewhere around the 1000. Whether it's this should be here somewhere. So the truth must be somewhere here, between the 750 and the 1000, or between the 1000 and the 1500. So if we would go on testing, we would maybe next try 900 and try to increase the thread number as high as possible, and look what we get. So in this case, Blender has corrected the tile size. He will do this if we put this small hook here, because he says I can't make 64 threads if I have less tiles. So he has decreased the tile size. So he has 11 tiles in this direction and 6 tiles down here. So this means the real tile size that Blender took is now 7000 through 11 is 636. This means we have now a tile size of 636 and not 900. So in fact we are here with 636 and 64 threads, and we'll see what we get. How does the CPU? Looks okay. We'll see what we get. So we have the result with a tile size of 900, beziehungsweise it wasn't 900, it was 636 and 64 threads. We come only to 0651. So this is not our best result, and this means the truth must be in a larger tile size and with less threads. So I will go here to 32 threads, stay with 900 and let it render. And what do we get? We have the start here. The start looks okay. Okay, let's wait and see. On the task manager still looks promising. We are really up here on the 100% line, and this means we are rendering rather efficient. So we have the result. It's 6 minutes with 900 and 32 threads, and then we have 0600. So this is one of our best results, is nearly as good as 559 with a larger tile size. But it makes me think that the truth is possibly at 1200. Let's see. And then we need fewer threads. 16. Or 20. No, 20 is too much. I go down until 18. Now the thing looks good, and we make go. In the task manager, it looks rather okay, mostly. Now let's see how the end happens. It's going down. Now we are losing efficiency, but it's still rather high. So at the end we are paying the price for the larger tile size, because this is why we have here this end which is less efficient. But next I have an idea. We will try something. So first let's write down the result. And this is 553. We have 1200. And we have 18 threads. And we have 0553. And this is our best result until now. This is our best result until now. So the question is, which direction do we need to go? 1100 or 1300? But I want to do something else now. I want to test something else before we continue. I have seen that we also can make the horizontal and the vertical size of the tiles. So what I will do now is I will make them 7000 X size. No, doesn't want 7000. No, it doesn't. Can I set this to 0? Now he makes an 8. Okay, what if I say 7000 here? Then I remove this and I say I want 1000 here. No, he doesn't do that. That would be more interesting if I could change the X and Y size to different values. Okay, this he doesn't let me do that. Then we take a look on 1100. And again, we look how many threads we can take before we get a problem. Okay, 28 is the number. So 28 is the maximum number of threads we can take, and let's go. So let's see what we got. We got 614, also 1100, and we had 28 threads, and the result is surprisingly bad. 28 threads, 614, and this is really surprisingly bad. Is that really possible? Here 559, here 553, in between 614. Okay, I will decrease the number of threads from 28 to 24, and we will render again and we try if we really got this result. We go up to 100%. Let's see what we get. So looking into the task manager, we are nearly all the time on 100%. So from what I see now, I think we should get a really good result this time. So what we got is 622, and that is one of the best results. At least it's not a so bad result. Also, but it's worse than the other one with the 28 threads. So 1100, and we had 24 threads, and it was 0622. These are the results we got so far. And from this, the best result is still 1200 with 18 threads. Unbelievable. With 28 threads, it didn't work. With 20, yeah, okay, it was 1200. Possibly 1300 would be interesting. So, but we see where it's around. So we see where we need to go direction. Also, and we also see that we can influence the rendering speed by changing the tile size, and we also know that very small tile sizes do not really make sense. And this is the last thing I want to show now in this video. We will now render this with a very small tile size or with a smaller tile size. Let's say, for example, 256. And so you will see we land in completely different regions then, and it doesn't really pay out to use such small tiles. So we look in the task manager. We are not going to 100, we are around 80 a little bit. We'll see what comes out. As expected, we get a worse result, in this case 730, And now I will do the following. I will make 64 a rather small value, but I will increase the thread number to a high value, 64. And we will just look, and this is the last for today, how the task manager will behave when it's rendering. So, and what we see is what we had before. We don't go up to 100% here. So even, and this makes me wonder, with 64 threads we should definitely go up to 100%, but it doesn't. And because this is not the case, we will not have a perfect rendering result here. And this is the last result for now, and see you in the next video. So here we are back. The only difference I have done is that I have upgraded my PC from Windows 7 to Windows 10. We are here in Blender again, and we have the same picture like before. So we'll make a quick render test if everything works fine, and then we will see if there are differences with just between Windows 7 and Windows 10 at the current time. This is end of January 2016, and the version is Blender 2.76b. We are using render cycles, while often Luxrender is an alternative. Okay, let's look at the dragon. We have set dimensions very small, and we just make a quick starting render with the CPU with the default settings, and it works. So generally there is something. Now let me see what's the sampling actually. Sampling render 1. Okay, that's why it's really quick. Okay, let me do the sampling a bit higher to 5, 6, and let's see what happens. Okay, we see it's a little bit slower, but at this place everything is like it was before. So now we switch to the GPU. So we hope that the GPU will compute this faster. I press render, and these are the default settings. So it takes a while, then it starts rendering, but what we see is here OpenCL error CL-mem object allocation failure. So this is something new with Windows 10. Here also OpenCL-mem object allocation failure. So here we have this memory error, and we get this with auto tile size. So the problem is I can change to a smaller tile size now, and possibly it will render, but possibly it will not render, because the memory he has allocated here, he seems not to get it back until until Blender has been restarted. Okay, I will try it anyway. I will now go down to custom and make a smaller tile size, 128. Let's see what happens. And again we get OpenCL build failed errors in console. So what I'm doing now is I close Blender. Also exactly, I save the Szene. So right now I didn't do anything else than to restart Blender after we had this error. I leave the tile size on 128, which didn't work before, because I expect it to work now. So I press F12 for rendering, and as you can see, it's now rendering. And this is not under Windows 7, it's under Windows 10. So you need to remove the auto tile size sometimes. You need to make a smaller tile size, even so it's possibly slower, because somehow cycles cannot get the memory anymore. So now this was really fast, render some more samples, 24 for example. Let's look how long it takes. So, but most important is it works. The memory error goes away. You just have to restart Blender possibly and reduce the tile size to a lower level. Also by far you can't use anymore the 3000 you could use, or that I could use before. You have seen in the video under Windows 7. And this is something that's just different under Windows 10. I don't know exactly why, but this is the way how to get rid of this error, this memory error. At the moment, use a smaller tile size and possibly accept a slower rendering speed. So this time we needed 1 minute 24. We had a tile size of 128. I will now try a tile size of 64, and we will see. I expect us to be slower than 1 minute 24, but we'll just wait and see. So we are already at 3 minutes. That's nearly 3 times what we had before. And this means we will need, just like before, try to make the biggest possible tile size. Also we have 3 minutes 53 because of speed reasons. So smaller tile size, even under Windows 10, slower speed. But the problem is making too large tile size, getting a memory error. So if I switch to 256, I expect a memory error. We will just try. yeah, OpenCL memory allocation failure. So at this point, you can just close Blender and restart and use then 128. Now I would like to compare the CPU rendering speed with the 3 minutes 53 I had before with the GPUs. And for this, I look for a small tile size. Maybe I start with 32. So we are nearly at the end and we are below 3 minutes already. And this means 2 minutes 56. The CPU rendering was even faster than the GPU rendering if you make a too small tile size in the GPU rendering. So we are going to try something here. I'm going to try with the CPU rendering a smaller tile size, and let's see if we still will be below 3 minutes. So we are getting to the end here. And this is interesting. 2 minutes 50, we are 9 seconds faster with the CPU with the smaller tile size than we had been with the larger tile size. So with the CPU, sometimes it's quite opposite, that the smaller tile size is even better than the larger tile size. To verify this, I will now try the CPU with a tile size of 64. And if this really is the case, we will now get a result that is above 3 minutes. We will also take a look into the task manager to see the CPU usage in the rendering. And what we see here is that it goes really up and stays at 100%, which is normally just what we want. So we are getting to the end again. And the CPU curve was on 100% for all the time, what is just what we want. And the result should also be good. So unexpectedly, we are at 3 minutes and 7 seconds. That's within that range. Also, we did not have a lot of advantage or disadvantage having another tile size. So we can make one try, just for a try, and use 128 to see if that's going to be different or not. So the CPU goes up quickly to 100%, stays at 100%, that's good. So we are getting to the end now. And that is really unexpected. We are actually still below 2 minutes, really? Okay, what we see here now is that the CPU drops because some parts are not yet ready, but they are already in work by a core, and this means on the end, this is what happens if we take the larger tile size. Then we render at the end only with a few cores, and this is where we lose power. So the time shows 3 minutes 17, and this gives us the hint that when using the CPU renderer, the smaller tiles are definitely the better choice. Also for CPU, smaller tiles, and for GPU, as large tiles as possible. But we will make some changes at this place and take a look about it once more. So let's make another change and look if it will give us an advantage. I will now say custom and say X 320 and Y 32. Oh, he doesn't do that. What's the maximum he will do? But just a moment, let me try. X 16. Now he will correct this to 32, so he will not go below that. Okay. What if I say 8 here? This time he makes it. Okay, I will try this. I want to see what happens if I make a tile size of 8. So again, we get a good CPU usage. We run up to 100% and stay at 100%. So we are quickly coming to the end. We are still a bit below 3 minutes. But we will not beat the 3 minutes. We will be just on the 3 minutes. So a tile size of 8 doesn't bring an advantage. Looks like 16 is better. So I want to try to make here a 16. He doesn't do that. Okay. 11. He corrected to 9. 16. Okay, I make 32. No. Okay. PO. Also means maybe the best tile size for this is 16. Now we will do one more thing that we did in Windows 7. We changed the thread number because we are here always on 100% in the task manager. This may not really make sense, but we will just try that. Also I will make instead of 12 threads, which is native, I will make, let's say, 24 threads. That's twice as much. So 24 threads. And we will make a tile size of 16. And let's see if this changes anything or if we come what I expect around 3 minutes. So as expected, the CPU usage runs up to 100%. This is a good sign, so we will have the best possible render time with the CPU. We are quickly going to the end and we will see a surprise. Yes, 2 minutes 45. So this way, by adding more threads than normal, also here we earned 10 seconds. So what we try is to increase this. I will now make 32 threads. And I will make another change. I will say top to bottom here. And let's see if we get below 2 minutes 45 or not. So now it looks like this. We are running up, staying at 100%. This is perfect. And we are rendering top to bottom. My idea here about is that if we are rendering here in a line, possibly it may have advantages from the CPU cache, but that's just an assumption. We will see the result at the end, if this plays any role or not. So we are quickly progressing to the end, and the result is 247. So we didn't win much anymore, so twice the amount of cores seems to be the perfect number for the threads. So if you have 12 cores, take 24 threads. And the best size for CPU rendering seems to be, at least with my CPU, 16. And now the GPU rendering, what we see right now, seems to be a little bit of a lame duck under Windows 10 at the moment, because I had 2 minutes 47 with the CPU. If I tried it with the GPU with 128, and then let's see what we get. First we get a memory allocation error, so I go down to 64. Okay, I could restart Blender, then I can, oh, even then he doesn't get the memory. Does he get enough memory for 32? No, he can't. Also this means there is something wrong with the memory management here, and he doesn't release the memory somehow. I will now need to restart Blender, and then we can try a little bit more with the GPU rendering. So we are back, and what I did, I chose GPU rendering and a target size of 200 custom size, and let's see if he will do that. At least he starts rendering. So we are quickly going to the end. I think we will with this 200 tile size, of course, beat the CPU this time. So what do we get? Actually, we render the last tile with only one GPU, and we get 1 minute 12. That's roughly half of the time, a little bit less than half of the time than what we get with the CPU. Now if we take the standard values of 128, I expect to be a little bit below that, but we will see. So we are coming to the end, but we are already over the time we had before. We had 1 minute 12:45. This time we have 1 minute 24. And this means the rule that you should choose the largest possible tile size with GPU rendering stays, and is the best tip you can take here. The largest possible size you get only possibly by using custom, at least in my case. I will have to try what is still possible. For example, can I use 200? 28. So I have to find out what's the largest tile size that I can still use without running into this memory error, and then use this tile size for the renderings. So effectively, I think what he used was 240 by 160, and we have been faster. We are now just above 1 minute, and this shows again, the larger you can make the tile size, the better. The point is just 256 runs into an error. I will try 250. Will he accept 250? He doesn't change the numbers here. So if I don't make this, he will take 250 by 250. What will he do now? Okay, he will immediately run into this memory allocation failure, and this means in terms of GPU rendering, I will need to restart Blender. So for this time we are at the end of the video. What we have learned is, under Windows 10, something changed. Was it the drivers or whatever? I don't know. Normally I didn't change the drivers intentionally. Especially the rendering doesn't work as good as it was before. The memory allocation seems to be broken somehow. If you choose with GPU rendering a small enough tile size, you can still render 2 or 3 times faster as with the CPU. If you have 4 GPUs built in like me. If I would have only 1 GPU, possibly I would be, in my case, slower with the rendering than with the CPU. So this was my video about Blender and cycles, and just for fun we can switch to Luxrender for the end and try one rendering with that.